Hello and welcome to Physics Problems One by One.
So here is a problem. As always, read it, maybe once, maybe twice, and then pause the video and try to solve it yourself.
Last time I stopped when I counted the number of molecules that will hit the wing during time period delta t. So now all I have to do is to find the total force. And the total force is n, number of molecules that hit it, multiplied by this Fy. And what would be total lift? That's it. So F total equals, instead of n, I will write rho v s delta t, right? Sine alpha. Then I could do it in one step, but I'm not in a hurry. But then I have to put this, and I forgot, of course I forgot in this formula, multiply by Fy. And now, of course, I have to put Fy. I could do it in one step, but I do it in two. Rho v s delta t sine alpha multiply by this 2mv sine alpha cosine alpha divided over delta t. And remarkable thing happens, delta t will go away. It will cancel itself out. F total would be rho, and v would be squared, and s would be here, and m would be here, the mass of one single molecule. And then it would be sine squared. I will leave sine squared and cosine, like this. And of course 2 would be in front. And that's, I probably leave it at this. I say this is a total force. And I will wipe this out. And I say that in real life, of course, the collision is not elastic and there are a lot of other things. But so I will still say that total force, and this is remarkable, it is proportional to rho, to v squared, to s. There is some coefficient, because I don't know the mass of molecule, and I assume that molecules all moving with the same speed, which it is not. But this is basically some coefficient multiplied by rho, multiplied by v squared, and multiplied by s. And those are three most important things that are here. And let's first of all think it. We have a very simple model, I say primitive model, of molecules hitting the surface, being reflected, being deflected. They are deflected by certain force from the wing, they act on the wing, we calculate the projection vertically, we calculate the number of molecules that will hit us during time t. We have the result about the force that lifts the aircraft, and we have that it's proportional to rho, to the density of material, it's proportional to v squared and proportional to s. And this has remarkable consequences on a lot of things. For example, when this speed grows with v squared significantly faster than with s. So when we build a very big aircraft with a very big wing, with a very big s, and we have very small speed when we launch our aircraft in the air, let's say 100 kilometers in the hour, and then if total is enough to lift up in the air, we have mg, and we're flying up, mg is enough, this lift force is enough to lift us and to compensate for mg. But when our speed will grow, let's say from 100 kilometers to 200, what will happen? this v squared would be 4 times, and so the force that would be lifting us up would be 4 times more than mg. We will be accelerating up. It's not what we want. We want to fly steady. Fortunately, there are those things here like sine squared alpha and cosine alpha, and that means we can kind of tilt our wing, and this will kind of compensate for this force. So we position our wing, make the surface of the wing a little bit more horizontal, and the force will go down. But still, if we will accelerate from 100 kilometers to 1,000 kilometers, which is not a big deal, then 100 to 1,000, it would be 10 times more, but v squared would be 100 times more. If v squared would be 100 times more and s would be the same, this thing has to be manipulated very, very precisely to reduce the lift. So we have this dependency on v squared that creates a lot of real practical problems for real practical aircraft. I can talk about cruise missiles, but let's not go there because it's another level of complications. But generally speaking, this is a problem that shows that when the aircraft is flying with a small speed, this is the lift, and when the aircraft increases this speed, the lifting force increases significantly, because S cannot be changed. It's very difficult to change the shape of the aircraft while we're flying, although there was such Concorde, if you look, changing geometry, but it's complicated. And then, but you need to do it if you want to approach a very big speeds, very big velocities. But then sine and cosine can help you to change it. Well, another thing is that I was personally, not only this problem changed my attitude to physics, and eventually I loved physics way more than math, because exactly like those models, those primitive models that look like mostly like a joke, but nevertheless deliver remarkable results. I met this problem many times in my life, because I like to ski, I like to surf, I like to windsurf. And when we have, for example, a surfer that goes in the ocean and hits the water, the size of the surfboard is here, the angle of attack is here, the velocity with which he moves in the ocean is here. It's, if it's a windsurfer, he is zooming 40-50 kilometers an hour. And then this is the same force, but rho is not the density of air, but density of water. And this is very similar situation. Or another situation is skiing. Those skis are very old, they are very narrow. The surface of those skis is very small. This ski is not very good in powder conditions. When you have untouched snow that deep, then you need to float in this snow. And to float on the snow, what happens? You go down the hill and you accelerate and you're sitting underneath the snow, and then suddenly your speed becomes big enough and you suddenly pushed, the lift becomes bigger than your mg, and you push to the surface of the slope and you floating on top of the slope. And for that you need big S, and rho is something in the middle between the air and the water, because it's very fluffy, snowy condition. But the point is that still you cannot do it on those skis. The skis that I use to ski powder now are twice or even more than twice wider than this. And all of this to create big S. And so when S is bigger, the V that required, the threshold that required to reach the lift that equals your weight is decreased. So if you increase S twice, then V squared is decreased twice. And this V is square root of 2. So its square root of 2 is 0.7. So it's about 40% decrease in your required speed. So you go down, on those skis you have to go really very fast. Now on the wide skis you have to go 40% slower, and you reach the same lifting effort, lifting situation, and you fly and float. So this is a problem that I have a very intimate connection, so to speak, during my life. Another thing is that this approach of molecules that flying and hitting the wall, you will see it when we will be talking about ideal gas law or universal gas law, because those molecules that hitting the volume, the walls of this volume, and they all are moving, they're all moving because of the temperature, and they're all moving in all possible directions, and they have the all possible speeds. But if you assume that they're moving, 1/3 of them moving this, 1/3 of them moving this, and the 1/3 moving XYZ, and then 1/2 is moving this, so you have 1/6 of all molecules. And you assume that there is some V average that they are moving, so suddenly based on this logic, that each molecule hits the wall, and you count the number of molecules, you suddenly receive PV equal M mu RT, the universal gas law. And I will be talking about this not now, but later. What I want to say is that this is probably one of the most really physical problems. Physical in terms not like physical build up and muscle, but in terms of physics, the nature of physics that I will give here in those lectures, in those problems. So I hope you liked it. I hope you will come for more, and for that you subscribe, like, and I see you next time. Thank you.